Good afternoon. My name is Takayuki. I'll be presenting my talk on profile monitoring via eigenvector perturbation. It's been joint work with Drs. Barrientos, Chicken, and Sinha. A fundamental problem in statistics is determining if the data we observe is what we expect. There are many variations on this theme. For example, we can consider if functional data is what we expect it to be. And we can add on another layer of complexity by adding on a sequential aspect to this problem. So say we're at time step 1, we observe data, we perform this particular hypothesis test. We move to time step 2, we observe new data, we perform the same hypothesis test, and we do this so on and so forth. Now, to make this notion more precise, let's define a profile to be a noise-perturbed functional relationship that relates a set of predictors, in this case we'll assume it to be multivariate, and to a particular univariate response. And notice that this functional relationship f is constant for all time t. Now we'll adopt the following change point framework. Now say we've observed capital T number of profiles. We want to determine if all of those profiles are in a desired in control state, or if one of them is in an undesired out of control state. Now we'll formulate this by assuming that everything is in control up till time tau, and you'll see that here in that expression for y sub I t. And then everything after that is an out of control profile. So ultimately, the hypothesis test that we're performing here is shown in the bottom of that slide. Now that we have this task in hand, we need some measures of performance. So one such measure is called the in control average run length. And it's defined as the number of in-control profiles that you'll observe on average until you raise a false alarm. And this toy example, the average in-control run length, also denoted by an arrow not, is equal to 6. And conversely, you can consider the out-of-control average run length, which is defined as the number of out-of-control profiles that you'll observe on average until you correctly raise an alarm. In this case, the arrow 1, which is the common notation for the out-of-control average run length, is equal to 2. Now, for those of you more familiar with the traditional hypothesis testing on means, compare arrow naught to specificity. Think H naught for your null hypothesis. And arrow 1 is akin to your sensitivity. Think H1 for your alternate hypothesis. Now, in general, what we want is a large arrow naught and a small arrow 1. And typical values in the literature are shown here. Remember those, I'm going to come back to them. Now, if you combine traditional arrow naught values with streaming data, you're going to have a bad time. Because if you have, say, an arrow naught of 200, and you observe a new profile every millisecond, then on average, you're going to raise a false alarm every 0.2 seconds, which is unusable. Now, a possible fix is to arbitrarily increase that arrow naught, say, 1,000,000. Now you have a false alarm every 17 minutes or so, which is better. But arbitrarily increasing the arrow naught will also hurt your sensitivity. That is, it'll increase your arrow 1 to usually unacceptable levels. So the goals for this study is to create a computationally fast monitoring procedure for use in streaming data, and to have both a large arrow naught and a small arrow 1. That is to say, we want a low false alarm rate, and we want to be able to quickly detect an out-of-control profile. In terms of our model assumptions, well, who's to say that f is linear? So we'll assume f is nonlinear. And we may not even know what f is exactly, so we'll approach this nonparametrically. And we'll also assume that our predictors are multivariate. And I'll spend one slide on methodology. If you have more questions on this, because it is rather complicated, please come to the post session. Now, we'll assume here that the predictors are fixed for all time t. So we can consider the responses from W such profiles, so say the W most recently observed profiles, and we can compute a sample correlation matrix, which we'll denote by R. And since this is a square matrix, we can compute a leading eigenvector, we'll call that V. And since R is a random variable, we can compute its expectation, and we'll call its leading eigenvector V tilde. Now, the key idea in constructing our monitoring statistics, the thing we look at to determine if we're in control or out of control, is this, that V is approximately equal to V tilde. Now, in a scenario where all W profiles are in control, then the expected sample correlation matrix is going to look like a diagonal matrix with constant off-diagonal values. And the leading eigenvector is going to be the all ones vector. Now, since we have this key idea where V is approximately of V tilde, this quantity here, which we'll call the eigenvector perturbation, is going to be small in this case. Now let's throw in some out of control profiles into the mix. Now we have a two-block structure for our expected sample correlation matrix. The leading eigenvector is no longer the all ones vector. That is, say this vector is different from this vector. And because of our key idea that V should be close to this guy right here, when we compute this value is going to be large. So if this value here becomes too big, we're going to claim out of control. That's the strategy. Now let's just talk performance. So in terms of computational speed, our method is screaming fast because all you have to do is compute the leading eigenvector. And relative to the other methods in the literature with the same model assumptions, we blow them out of the water. Now, I would turn back to this slide by add on another column to that table. For the arrow knot and arrow one performance of the eigenvector perturbation control chart, we were able to achieve a lower bound on the arrow knot of 7 million. Now that in and of itself is not special. What is special is the fact that the arrow knot is equal to 1, aside from some pedantic examples. But even those pedantic, extremely tough scenarios, we get an arrow 1 on the order of 10, which is still really good. This is a win. Now, in terms of a performance summary, we've met all of our performance requirements. We've met all of our model assumptions. The problem is, though, that this comes at the cost of a strong assumption on the fact that the predictors cannot change during monitoring. So future work involves being able to relax that assumption to allow predictors to change during monitoring. Thank you.